we can store elastic potential energy in a spring when we stretch or compress it. So we shall consider below. Okay, so we have a mass m on the end of a spring of spring constant k. So we shall compress, we shall, let's say, stretch this spring and then release it. And so when we stretch it, we store energy in it. When we release it, all that elastic potential energy is going to be converted into kinetic energy of the mass as it slides along on the surface. And so we can calculate, for example, the change in speed. So we can say it has an initial speed and a final speed at different points in its motion. And so that will correspond to different amounts of potential energy stored in the spring. Okay. So we consider a mass m at the end of a spring of spring constant k. So when we stretch the spring, we store elastic potential energy. When we release it, the elastic potential energy is converted to kinetic energy of the mass. And we are working on a smooth surface, of course, so we are assuming that there is no energy loss. So we have the mass initially this way. This is xi, and then we stretch it to a certain point here. Let's say let's say this is x0. So we shall say this is x final. And so at some point here, actually, hold on a second, let me do it a different way. X0, let's say this is x1. And so we stretch it, and when we release it, this is what I want to do. So we release it, and so at this point here, we can say this is x initial. At some point here, we shall have x final, and this will be v initial, v final. Okay, so the spring will transfer its energy to the mass, so the mass will have a certain v initial and a certain v final in between the points x initial and x final. Okay, so the way this works, of course, is suppose we apply Newton's law. So we know that the force applied is equal to k times delta x, where delta x is equal to x final minus x initial. And then we are saying that this force is equal to m times acceleration, which is dv dt. So in this case, F is equal to m dv dx times dx dt, like that. That's our applied force. And then we are saying that mv dv dx is equal to k delta x. So we can write mv dv is equal to k. In this case, let's put the delta x to be equal to x final. Let's do x1 minus x0 dx, and then we shall integrate from initial to final, and then integrate from v initial to v final, and then we have half mv squared v initial v final equals k x1 over 2 squared, where we can take x0 to be 0 to simplify everything. And so we shall have half m v final squared minus half m v initial squared equals k x final squared over 2 kx initial squared over 2. So this is for the applied. So the change in kinetic energy of the mass is equal to the change in elastic potential energy of the spring for applied force. And we can of course do this for the spring force also. The spring, if you use the spring force instead, the difference is that it will just switch. It will just be K initial squared over 2 minus K final squared over 2. Okay, so we shall say that, recall that FA is equal to minus Fs. Therefore, if we used Fs equals minus K delta X instead of F equal FA, which we used, we arrive at the same result but switch sign. So for example, what we would have then would be half mv final squared minus half mv initial squared equals kx initial squared over 2 minus kx final squared over 2 for Fs. Okay, so we have two things going on there. We have the applied force, which is equal to the spring, the negative of the spring force. The negative of the spring force is Hooke's law force, which is equal to minus K delta X. The applied force is equal to K delta X. So that's the difference. There's just a difference in sign. Any questions at this point? So let me see where we are now. Okay, so let's do an example on this before we go on. So what I'm describing is something like this. You've all seen this toy gun. If you have a kid, brother or sister at home, they have a spring in there like that. Okay, and so you're going to compress a dart in the spring, and then you fire it, and it shoots the dart out. So the question then is, what is the speed of the dart as it leaves the gun? Okay, so you've compressed it to a certain displacement delta x, so you want to just find the speed of the dart as it leaves the gun. So work on that. I've given you all the information I think you need for this. Spring constant, let's say the spring constant is 50 newtons per centimeter. Let's make it 500 newtons per centimeter. So I think you have everything you need. Okay, so let's look at the solution. Okay, so what do we have for the speed of the dart? Anyone? 200 what? 637?
No, 63.
Okay. Anybody else? So what we have then is we have the compressed dart in a gun like that. So we know that initial position is equal to 0, since I said that it was at the reference point. V initial is also equal to 0. So it is compressed to 50 centimeters. Is that what I said, or is it 20? 20. Then we want to find V final. Okay, so you can use the formula that I gave you, half mv final squared minus half mv initial squared equals half k x final squared minus half k x initial squared. And you can just eliminate some of these quantities, so we can have half m v final squared equals half k x final squared. Remove the halves, so v final squared is just equal to k x final squared divided by mass. You can take the square root of that to get v final, which is the square root of k x final squared over m. So then you plug in the quantities that you need. So we have 500 newtons per centimeter divided by 50 grams, which is 0.05 kilograms. Multiply that by 200 by 20 squared, which is 200, which is 400 centimeters squared.
Convert it into.
You can convert to meters, but not necessary, like that. So V final. So you can do the calculation and see what that gives you.
2,000.
What?
2,000.
Total? After you calculate is 2,000?
Yeah.
Okay.
2,000.
So everybody good with that? 2000 centimeters per second, which is equal to what? 20 meters per second. Questions on that? So let me remove this.
So you didn't have to change centimeters to meters.
You can if you want at the beginning, but I knew it was going to cancel. Some of them was going to cancel at the end to end up at centimeters per second. I can just convert it at the end. So it doesn't make any difference whether you convert it before or after. It will still give you the same result.